Hi everyone. So in the last video, we introduced this idea of the derivative function. And so the idea was that rather than individually calculate the slope of the tangent line at every separate x value, instead you can calculate this general derivative function, which will tell you the slope of the tangent line at any x value you want. So let me just write that down again and remind you of how you actually calculate it. So if f of x is a function, then f prime of x is called its derivative function. Or you might just call it its derivative, like later on in the class, that's what we'll probably say, is its derivative function. And so the derivative function is a function just like any other function, right? You can graph it, you can plug numbers into it. Once you calculate the derivative, you have a formula that you can just treat just like any other function. And so the way, what's like the purpose of the derivative function? Well, it kind of like carries this information about the original function. And specifically, the information it tells you is that when you plug in different x values, the outputs that come out tell you the slopes of the tangent lines of your original function. So f prime of x tells you the slope of the line tangent to f of x. And then maybe just to kind of phrase this another way, because we didn't really use this word in the last few videos, but it's still something that you should be aware of. The slope of the line tangent to f of x, another way of saying that is the instantaneous rate of change. So I just want to write that down as well. So that's going back to the very beginning of the quarter. We talked about how instantaneous rate of change is basically the same thing as the slope of the tangent line. And it tells you those things at any x value. And so how do we actually calculate the derivative function? Well, we use the equation or the limit. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And so this looks exactly like the formula that we used in the previous video, except for that instead of plugging in a specific number for x, we're going to leave the x there as we compute the limit. And so what will result is a function that still has x in it, and then you can plug in different x values after doing the limit. So really the only difference is that earlier we were plugging in different x values before doing the limit, and therefore we had to do it individually for each x value. Now we're doing the limit only once and plugging in different values for x after taking the limit. So I want to do another example that we'll kind of use as a jumping off point. So in this video, we're basically going to be talking about some of the stuff from last time, basically looking at the graphs of the original function and its derivative function and kind of making some connections about, again, whether the function's increasing or decreasing and what that tells you about the derivative. And then there's also just a couple of other odds and ends that we're going to discuss in this video as well. So the first example I want to do is let's let f of x is equal to x cubed. And I want to find f prime of x. So this might be a good time to pause the video and try it yourself, and then resume to check whether you got the right answer, but I'll go through it as well. Okay, so we know that in order to calculate this, we're going to have to do f of x plus h, right? So that's something that you probably want to do ahead of time so that you can just kind of put it into your limit when you're ready. So what is f of x plus h going to be in this case? Well, it's going to be x plus h cubed. And another way of writing that would be x plus h times x plus h times x plus h. And there's a few different ways of multiplying three things together like this, but probably the easiest way is to first multiply two of them together and then multiply the other one in. So I'm going to leave one of the x plus h's out. And then we already saw in the previous video actually that if you multiply two of them together, you get x squared plus 2xh plus h squared. And so now if we multiply x plus h with all of this, we're going to get x cubed plus 2x squared h plus h squared x plus x squared h plus 2xh squared plus h cubed. And let's see, do we have any common terms? It looks like we have a couple, right? We can put together, we have a couple of 2x squared h's and a couple of h squared x's. So this all together simplifies to x cubed plus 3x squared h plus 3h squared x plus h cubed. Okay, so let's put that into our limit now. So we're trying to do the limit as h approaches 0 of f of x plus h. So now we can put in what that is. So that's what we just found over here. So x cubed plus 3x squared h plus 3h squared x plus h cubed. And then from that, we're supposed to subtract f of x, right? And so what is f of x? F of x would just be x cubed. And then we're dividing everything by h. So the x cubed here cancels out with the x cubed here, right? And so we're left with the limit. And I have a couple of graphs hiding down here, but I'm going to scooch them down so we can look at them after. Ooh, it's a behind the scenes glance. Sorry about that. Just going to move these down a little bit. Okay, so now we're left with the limit as h approaches 0 of 3x squared h plus 3h squared x plus h cubed, all divided by h. And so now we can factor out an h from everything. And so we're left with 3x squared plus 3hx plus h squared, all over h. Cancel out the h's, and now we're going to be left with something that we can actually plug the 0 into, because now we'll just have 3x squared plus 3hx plus h squared. And now we can plug in 0 for h, and basically what will happen is that we'll get 3x squared plus 0, which is equal to 3x squared. So basically what we just figured out is that the derivative function of f of x is equal to x cubed is 3x squared. So just again to remind you, how this works, like let's say, for example, you wanted to find the slope of the tangent line at 1. So if we wanted to find the slope of the tangent line at x is equal to 1, well, now that we have this formula, we can just plug 1 into this formula. So we would have 3 times 1 squared, and it would be 3. So we know that the slope of the tangent line at 1 is equal to 3, and you could plug any number you wanted to into that. The most kind of frustrating mistake I see students make in this section, and I guess it's not really a mistake, but I've definitely seen on like a test or something where I might ask you first to find the derivative function, and then maybe I ask you to find the slope of the tangent line. And I've seen people actually answer this question by going back and doing the limit all over again, but with a 1 instead of an x. And that's just a waste of time, because once you have this formula, you can just plug stuff directly into that. And that's kind of the whole point of it. Okay, so I want to look at the graphs of the original function and its derivative again, and just sort of remind you of some kind of connections between the two graphs. So the first one I just want to remind you is like just generally how you can really read and make sense of the derivative function. So the way that you want to look at the graph of the derivative function is you want to think of all of the y values, all of the outputs of the derivative function as telling you the slopes of the tangent lines of your original function. So for example, as we saw above here, right, when we plugged 1 into the derivative function, we got 3. And so that means that the point 1, 3 lies on the graph of the derivative function. And what does that tell us about the original function? Well, it tells us that when we go to an x value of 1, if we were to draw the tangent line at this point, that the slope of the tangent line at x is equal to 1 is 3. Right? That's exactly what, because there's this point 1, 3 on the derivative function, that tells you that the slope of the tangent line on the original function is 3. And same goes with any other point on the graph, right? So same thing at -1, right? If we go to a point of -1, on the derivative, that also has a y value of 3. And so what that means is that if we were to go to the point at -1, on this function, it would have the same tangent line slope. And that makes sense, right? If we draw this tangent line, it looks like it's the same slope as the one at 1, right? And it's basically because of the symmetry of this graph. So one thing that you'll probably notice in this class when you're looking at the graphs of functions and their derivatives is that if the original function has some sort of symmetry, the derivative function is also going to have some sort of symmetry. And it might not be really the same symmetry, but you can definitely make some connections between how the graphs look. Okay, so I'm going to bring up the same graphs again, but I want to do something a little different with them. And this is something we talked about in the last video, but I just want to repeat it again. So remember that we talked about this connection about when the original function is increasing, that means that the derivative function is positive. And when the original function is decreasing, that means the derivative function is negative. And I'll write those down as facts in a moment, but I first want to look at how that shows up in this graph. So if we look at the graph in black here, it's always increasing, right? Our original function, it's increasing. I shouldn't say always, there's one exception. So it's going, if you're kind of tracing from left to right, it's going up, it's going up. The one place where it's neither increasing nor decreasing is at 0. So the graph kind of flattens out a little bit, right? It kind of briefly takes a pause and has a slope of 0 actually at that point. But then right after that, it starts increasing again. And so what connection can we make to the derivative function? Well, the derivative function, notice it always lies above the x-axis, except for at 0. So this is the only point where the derivative is equal to 0. If we look at the other parts of the graph, they're all positive. And again, I want to just really emphasize that when I say the word positive in this class, all I mean by that is that the graph lies above the x-axis. So when we're talking about a function being positive, it doesn't matter whether that function is increasing or decreasing. We just literally mean it lies above the x-axis. So it's really easy to get confused between increasing and positive because, as we can see, there is a relationship when you have one function and its derivative. But if you're just talking about one function at once, when you say the word positive, you mean above the x-axis, and when you say the word increasing, you mean it's going up from left to right. So they're two distinct ideas. So I want to write down that kind of fact in general, and this is going to be a really important fact to know about derivatives, and it's something that we'll come back to in a little bit more depth later in the quarter. So if f of x is increasing, the derivative f prime of x is greater than 0. And so again, when I say greater than 0, this means it lies above the x-axis. And if f of x, the original function, is decreasing, then we can say that the derivative is negative. In other words, it lies below the x-axis. And then if f of x is neither increasing nor decreasing, so it's kind of like temporarily flattened out, then f prime of x is equal to 0. And what would that look like on the graph? Well, that would mean that it lies actually right on the x-axis, right? Because when you have a point that's on the x-axis, that means that its y value is 0. So why is this? I mean, we saw that it's true in this picture, but really the reason this is true just goes back to what the derivative tells you. So the derivative tells you the slopes of the tangent lines, right? And so when a function is increasing, we saw that, for example, at 1, we had this positive slope, right, of positive 3. And so that means that the derivative is going to have a point at a height of 3. And so that point is going to be above the x-axis. Okay, so I want to kind of use this idea to do kind of a practice problem that basically just kind of tests whether you can apply this idea. So this graph that I've graphed here, you could write down the equation for it, but let's not do that, right? We're just going to kind of gather information from this graph just by looking at the graph without trying to figure out what its equation is. So let's say that this graph here is the derivative of some mystery function. And we're not even going to figure out what that mystery function is. We're just going to use this graph of the derivative to see what we can figure out about the original function. So let's say, suppose g prime of x, that is the function graphed, is the derivative of some mystery function g of x. And so just by looking at the graph of the derivative, I want to answer the following questions. So first question is, on what intervals is g of x, the original function, increasing? So how can we answer this question? Well, it goes back to what we just wrote above, right? What we said is that a function is increasing when its derivative, I didn't mean to go for the rainbow one, but I'll just stick with it. When a function's increasing, its derivative is positive, right? So if the question is to figure out where is the function increasing, that means we want to figure out where is the derivative positive. So what part of this derivative function lies above the x-axis? Well, this part, right? And we can assume that, by the way, that this graph keeps going in either direction. So let me kind of summarize that. So basically what we just said is that when g prime of x is positive, g of x is increasing. And so on what intervals is this derivative function positive? Well, assuming that the graph keeps going to negative infinity on the left, the graph g prime of x is positive from negative infinity up until 3, right? Not including 3, because at 3, it's actually equal to 0. So maybe I'll circle this a little bit less close to 3, right? So that's our answer. That is, without even looking at the graph of the original function, without even knowing what the original function is, just by looking at the graph of the derivative, we can say, oh, okay, well, that's the part of the derivative that's positive, and that tells us that the original function is increasing at that part of the graph. And we can even get more specific. So, for example, if you were to look at, let's say, this point here, so we can see that the point 2, 2 lies on the graph. And so that tells us that whatever the original function g of x looks like, the slope of the tangent line at x is equal to 2 is 2, because that's the height on our derivative function. And the slope at x is equal to 1 of our original function is 4, because that's the point that lies on the derivative, 1, 4. Okay, so the next question is on what intervals is g of x decreasing? Well, it's really kind of the same question, but now just looking at when is the derivative negative, right? So when the derivative is negative, g of x is decreasing. And so we just want to look at this graph and see, okay, what part of the graph is negative? What part of the graph lies below the x-axis? And so this is the part of the graph that lies below the x-axis, right? So g prime of x is less than 0 on the interval from 3, not including 3 because it's actually equal to 0 at 3, to infinity. And so that answers our question. That is where the original function will be decreasing. So again, just to give a quick example of like a specific point. So on our derivative function, we have the point 4, -2. And so that tells us that if we had the graph of our original function, the slope of the tangent line at 4 would be equal to -2. And so it would be decreasing, right? And same goes with any other point in this part of the graph. And then the last question we can answer is, at what point is g of x neither increasing nor decreasing? So looking at the graph, now we're looking for where is the derivative equal to 0, right? And the derivative is equal to 0 at x is equal to 3. So when the derivative equals 0, g of x is neither increasing nor decreasing. And so g prime of x is equal to 0 at x is equal to 3. And so you can kind of imagine what the graph of g of x would look like without actually kind of drawing it. It would be something that starts by increasing, then flattens out, and then goes back down. So maybe it looks like a parabola, right? And actually, I happen to know that the original function for this one is a parabola, but even without knowing the specific shape, you could definitely know that it starts by going up, right? And then flattens out and then goes back down. And so this is a really, really powerful idea, this fact that like, you don't need to know what the original function is in order to kind of know information about your original function. So we'll see a little bit later, I'm not sure in how many videos, probably in like 3 videos or 4 videos, how there's an application of all these ideas to physics, to talking about the position function of an object and then its velocity function and its acceleration function. And so basically, without knowing exactly what the position function of something is, if you know its velocity function, that can tell you things about the motion of the object. And so that's kind of the real world application of what we're doing right here. Okay, so a couple more things in this video. The next one is just sort of a technicality that we need to bring up if we're talking about taking derivatives. And so this is something called differentiability. So it turns out that not every function has a derivative function at all x values. And so we're going to talk about like what needs to be true in order for a function to have a derivative. So the word for this is that a function f of x is called differentiable at x is equal to a if basically f prime of a exists. So differentiable just basically means like you can actually take the slope of the tangent line. And so, right now I'm just telling you this as a definition, right? So the word differentiable, when you see that, just think of it as the derivative exists. So in what kind of situations will a function not be differentiable? Well, we'll go through those right now. So f of x is not differentiable at x is equal to a if any of the following things happen. So the first one is that it's not differentiable at a if f of x is not continuous at x is equal to a. And so this could be, the situations that we'll most likely see for this would be things like a hole or a vertical asymptote, things like that. So just to kind of sketch a quick example, if you had a function that looked like this, and let's say that this vertical asymptote happened at x is equal to 2, this function is not differentiable at x is equal to 2. And so why is that? Well, basically, most of the situations that we'll be seeing, if a function is not continuous, it's also not even defined. So this function, if there's a vertical asymptote, the original function doesn't even have a point at x equals 2, right? Like, if there's a vertical asymptote or a hole in your graph, that means that there's no information at that specific x value on your graph. And so there's just like no way that you could even draw a tangent line because there's no point on the graph. But there are some other situations where a function is defined and is continuous, but it's not differentiable. So that's the other 2 points that I want to bring up here. So the next place that this could happen is if your function is, or I should say has, a corner or something that's called a cusp at x is equal to a. So basically what I mean by that is if you have something like that looks like the graph of absolute value of x, right? So absolute value of x is not differentiable at x is equal to 0 because it has a like a corner in the graph. And then what does the word cusp mean? Well, a cusp basically kind of looks like a corner, except for it's like, I'll just show you in a picture. So something that looks kind of like this. So this is what the graph of actually f of x is equal to x to the 2/3 is like the graph that I drew on the left. So this would also not be differentiable at x is equal to 0. And so what would happen for these types of equations is that basically you could come up with a derivative, but the derivative just wouldn't be defined at that place where the original function was not differentiable. So that's actually one of the things I ask you to do on the worksheet is to figure out what the derivative function is for the absolute value function. And part of what your derivative should include is that it should not be defined at x is equal to 0. So there will be, you could take the derivative here or here or here or here at like basically any of the other points. So the derivative function will exist, it just won't be defined at 0. And then same thing for this one in magenta. Okay, one more. Keep using up more space than I expected. So one more thing, or one more kind of condition during which a function might not be differentiable is if f of x has an endpoint. At x is equal to a. And so we saw an example of that actually yesterday. So the graph of square root of x. So if you have the graph of f of x is equal to square root of x, that function is not differentiable at x is equal to 0. So I kind of forgot to explain why on these last two, the function's not differentiable. And basically it's because when you have when you're finding the derivative is equal to the slope of the tangent line, right? And so it just doesn't really make sense to find the tangent line at a corner, right? Because you could kind of draw it like any way you wanted. Whereas when you have a function that, say you're looking at like this part of this function, there's really only one way to draw the graph to follow its shape, right? Whereas if you have this sharp corner, it's just like kind of unclear like where exactly the tangent line should go. And so it's just undefined. There's just no clear defined way to find the slope of that tangent line. And then similarly with an endpoint, like you just wouldn't really know where to put it, right? Because like you could kind of like picture that the tangent line has to kind of hug along the shape of the graph. It just wouldn't be clear where that would be if that was at like the very end of a graph. So that's why these certain circumstances are not differentiable. So just to give a quick example, so here is some function I cooked up. So let's try to come up with what are the values where, or what are the x values where this function is not differentiable. So let's say this function is called f of x. So this function f of x is not differentiable at, so it's not differentiable at x is equal to -2 because that's an endpoint. It's not differentiable at x is equal to 1 because that's a corner. So it's like a sharp corner. There's no derivative there. It's not differentiable at x is equal to 2 because there's a hole. It's not differentiable at x is equal to 4 because there is a cusp, right? That looks more like that shape from that earlier one. And then you have another cusp shape actually at x is equal to 6. So this function has a lot of problems. I mean, I made it specifically so that it would have a lot of problems. What else do we have? Well, x is equal to 7. That's a vertical asymptote. And then the last one would be x is equal to 9. And so that would be because it's another endpoint. So this stuff will actually not come up that much. It's more like a technicality that you just have to be aware of. For the most part, when you take the derivative of a function, if it's not differentiable at a specific x value, it will just kind of come out that the derivative won't be defined at that x value. And we'll see some examples of that in the future. Actually, we already saw an example in yesterday's video. So when we did and I don't have the picture of the graph pulled right up, so I just go back to the last video if you're curious about this. But so we had the function f of x is equal to square root of x. And so we knew that that function was not differentiable at 0. And so if you look at the graph of the derivative actually has a vertical asymptote at 0. So basically, when the original function is not differentiable, the derivative will be undefined. So the derivative of square root of x was normal everywhere else, but at 0, because this function is not differentiable there, the derivative function had a vertical asymptote. It was undefined at 0. Okay, couple more things in this video. I know it's kind of a grab bag video, but there's one other important fact that we need to get out, and then I just want to do a little bit more practice with kind of comparing the graph of the function and its derivative. So the other important fact I want to talk about is the derivative of a linear function. So this is something that actually we talked about at the very beginning of the quarter. So remember in the very first video, we talked about how one of the purposes of calculus is to be able to find the rate of change for any type of function. And one of the things that I said in the video is I said, well, a linear function, you don't really need to use calculus to find its rate of change. So why is that? Well, for a linear function, the rate of change is just the slope. And so you don't need to do any calculus to answer the question of what is the derivative of a linear function. You just have to find its slope. So let me kind of summarize that. If you have a linear function, so a function that looks like mx plus b, then its derivative is just going to be equal to m. So for example, let's say that we have the function f of x is equal to negative 5x plus 1. So I'm just going to roughly sketch that. So if this is our function, let me make that a little better. So negative 5x plus 1 might look something, I'm just going to do something rough here. So maybe something like this, has a negative steep slope and it has a y-intercept of 1. So the slope of this line is 1, right? And so that means that no matter where you go, the instantaneous rate of change is the same, and that instantaneous rate of change is equal to negative 5. This is kind of a weird thing to picture, but if you had to actually draw a tangent line to a linear function, it would just be the line itself. We don't really talk about drawing the tangent line to a line because you don't need to use tangent lines to find the rate of change. You can just say, oh, it's just the slope of the line as it is. But just so you know, as kind of a technicality, if you were supposed to find the slope of the tangent line, the tangent line would just be overlapping with the line itself. It just would be the same as the original linear function. So what would the graph of the derivative look like? Well, what is the graph of, so what is the derivative of negative 5x plus 1? Well, we just said that the derivative is just going to be equal to the slope, right? So the derivative function is going to be negative 5. So what is that graph going to look like? Like if someone just asked you to graph y is equal to negative 5, that would be a horizontal line at a height of negative 5, right? So that this is what the graph of the derivative would look like. So why does this kind of graph make sense? Well, notice that no matter what x value you go to on the derivative, it's always at the same height, right? No matter what number you plug into this derivative function, you always get negative 5. F prime of 1 is negative 5, f prime of 2 is negative 5, f prime of negative 3 is negative 5, f prime of 100 is negative 5. That's the way constant functions work. No matter what x value you plug in, you always get the same output. And so why does that make sense? Well, if you look at the linear function, it doesn't matter what point you're going to, the slope is always the same. Whereas for a function that, looks more like this one, let's say, the slope is all over the place, right? It goes down, it goes up, it does all different things. And so its derivative function would have different values. Whereas here, the slope is always negative 5. And so that's why the derivative function is a constant function. So let me even make a note of that. So the derivative function is going to end up being a constant function. So a constant function is a function whose graph is just a horizontal line. All right, one more thing, and I know that there's been a lot in this video, but most of it is, really the only things that were kind of new facts were, the definition of differentiability and then the derivative of a linear function. Everything else is just kind of practicing to get some comfort with working with the derivative. So the next thing I want to do here, this is a pretty challenging question, but I want to go through it anyway. So what we're going to do is we're going to look at the graph of a function. So this is a graph of a function called f of x. We're going to do our best to sketch the graph of its derivative. Without knowing what the equation is for the function and using the limit definition, we're just going to kind of try to eyeball it. And this, again, I'm going to warn you, this is really challenging. I think a lot of students find this really difficult, but the main thing to keep in mind when we do this is that I'm not looking for perfection. I'm just looking for kind of a few key features, and I'll explain what that looks like in a moment. So basically, we're going to use the graph of f of x to sketch the graph of f prime of x. So the easiest way to start on this is to start by looking at where is the derivative going to be equal to 0. So where on our original function do we have a horizontal tangent line? So first step is, where does f prime of x equal 0? So we can see that we would have a horizontal tangent line at x is equal to 0, right? So that's one place where the derivative is going to equal 0. Another place where we have a horizontal tangent line would be at x is equal to 1. And then another place where we have a horizontal tangent line would be at x is equal to 2. And so what does that mean? What does that tell us about our derivative? That means that the derivative is going to go through a height of 0 at those x values, right? Because remember, the heights of the derivative function correspond to the slopes of the original function. Height of the derivative equals slope of the original. So if the slope of the original is 0, then the height of the derivative should be 0. And when the height of a function is 0, that means it's going through the x-axis. And so the next step is basically to figure out, where is f prime of x greater than 0, and where is f prime of x less than 0. Well, and we're not necessarily going to write that down as an answer using intervals. I just want to kind of eyeball it and see if we can fill in the function from that. So if we look at the original function, it's increasing from negative infinity. So let's assume that this graph keeps going down here and here. So it's increasing from negative infinity until x is equal to 0, right? All the way up until 0, the graph is increasing. And so what does that mean about the derivative? That means the derivative should be positive. Maybe I will. Let me write down these intervals. I think that might be helpful. So the first interval where the derivative is going to be positive is from, didn't really think this through. Let me do it like this. So where is the derivative positive? Well, we saw from negative infinity until 0. Where else is the derivative going to be positive? Well, the next part of the graph that's increasing is from 1 to 2, right? And so when the original function is increasing, the derivative is positive. And so from 1 to 2, the derivative is going to be positive. And that's it, right? Those are the only, here and here are the only parts of the graph that are increasing. And so those are the only parts where the derivative is going to be positive. And then the last question we want to answer is, where is f prime of x negative? And so now we're looking for where is the function decreasing. So it's decreasing from 0 to 1, and then it's decreasing again from 2 to negative infinity. And so the answers here are going to be, like we just said, 0 to 1, and from 2 to infinity. Okay, so now that we have that information, now we know a little bit of how to fill this graph in, right? So we want to make sure that the graph of the derivative is positive. So literally when I say positive, I just mean above the x-axis all the way up until 0. And so that means it's going to look something like this. Oops. Right? That's a graph that is positive. It's lying above the x-axis. And then what happens between 0 and 1? Well, in that part, the derivative should be negative, right? Because the function is decreasing. And so that means that the derivative needs to go below the x-axis. And let me fix this a little. I feel like I didn't draw this very well. Okay, more like that. And so that means that the derivative should now go below the x-axis, right? Because it's supposed to be negative. But then it has to come back up, right? Because it's supposed to equal 0 again at 1. So we're just going to make it go down and then come back up. And then what's supposed to happen between 1 and 2? Well, we said that between 1 and 2, the derivative is positive again. And that's because, again, the function is increasing. And so that means that we're going to make the derivative go up, but then it has to come back down again, right? Because we know that it's supposed to hit 0 again. And so it couldn't just keep going up because it's supposed to hit 0 again. And then what's supposed to happen from 2 on? Well, from 2 on, we said that the function or the derivative should be negative. And so that means that the derivative needs to now be below the x-axis, and so it goes down like this. And it'll keep going up this way. So just a rough sketch. If you were doing this on your own and you sketched it a little different, that would be okay. Really, all I would be looking for is basically that you answered these 3 questions correctly. So you should be drawing a graph that is equal to 0 at the places where the original function has a horizontal tangent line. You should be drawing a graph that is above the x-axis wherever the original function is increasing. And you should be drawing a graph that's below the x-axis wherever the original function is decreasing.